Hello all, my name is Abhijit and welcome to the topic impact of Doppler on narrowband and wideband waveforms. Narrowband signals find applications in radio communications while wideband signals find applications in underwater acoustic communications. So now in this paper we are dealing with the Doppler tolerance of signal using narrowband and wideband ambiguity functions. So ambiguity function is basically a two-dimensional autocorrelation of waveforms in time and frequency. So the x-axis will be the time delay and y-axis will be the frequency shifts. We will be dealing with four kinds of signal, frequency modulated signals that we will discuss later. Let us discuss the narrowband ambiguity function definition. So this is the narrowband ambiguity function definition. U of t is u of t will be our signal, and ft will be the Doppler shift. Here the important point to note is that here the Doppler is modeled as a frequency shift, that is e raised to minus 2 pi ft t, and this is the wideband equation. Here eta represents the time scaling factor, that is 1 plus v by c. V is the radial velocity, c is the speed of sound. And here the important thing to note is this Doppler is modeled here as a time scaling operation, that is the signal can be compressed or expanded. And so these are the signals we use in our experiment to analyze this ambiguity functions. So these are the signals are linear LFM, logarithmic FM, then quadratic FM, and hyperbolic FM. And these are the equations for the same. Here Fc represents the center frequency, B is the bandwidth, T is the sweep time, and small t is the instantaneous time. And these are the spectrograms of the signal that we generated. So our signal band is 5 to 11 kilohertz. So this is a linear, this is the spectrogram of LFM, and this is the spectrogram of logarithmic FM, and this is for quadratic FM, and this is for hyperbolic FM. So now we'll pass these signals through this narrowband ambiguity function definitions and wideband ambiguity function definitions, and we'll analyze the signals on both the contexts. And this is the ambiguity function for obtained with a narrowband definition for the LFM signal. So this is a 3D plot, and this is a mass filter output. So here you can see a red curve that represents the mass filter output for time delay 0 and frequency delay 0, and this green curve represents an intermediate time shift and delay, that is 7.5 milliseconds and frequency delay of 1 hertz, and this blue curve represents the time delay of 15 milliseconds and 2 hertz. So we have this blue curve is the extremum time delay, so that we are varying this delay from minus 15 to plus 15, as well as frequency from minus 2 to plus 2 hertz, and correspondingly 2 points, 5 points we are plotting. And this is the mass filter output as well as the 3D curve of that logarithmic FM, and this is for quadratic FM. So the here when we observe we will see like almost the patterns are similar in these 4 cases. One more important point is that if the time shift is 0 and frequency shift is 0, we will get a maximum peak value for the mass filter output, and when the time delay is increased, or with a time delay, this peak is getting shifted to the right or left based on positive or negative values we give. And for the frequency shifts, what we observe is the peak value of the peak is getting reduced. So that is the main observation from this ambiguity function using this narrowband definition. So for frequency shift, the peak of the mass filter is getting reduced, and for time shift, the location of the peak is getting changed. So in our experiment, we are varying the frequency from -2 Hz to +2 Hz, as well as the time shifts we are varying from -50 milliseconds to +15 milliseconds. A similar observation was done with this wideband ambiguity function definition, and what we observed is for time delay of 0 and velocity, that is the radial velocity in wideband case, 0 milliseconds, 0 meter per second, we get a maximum mass filter peak. Then when we added a time delay, this peak is getting shifted, but for this compression or expansion happening due to the compression or expansion happening in the signal, we are not getting the peak as a peak, rather it is getting spread out. And one more important point is there is no symmetry between the peaks, and if based on that is eta, if the radial velocity is getting increased, then the spread of the peak is also getting increased. That you can see from the 3D plot, that is in the far end, the spread is also getting increased. That is same as the mass filter output also. And in the case of logarithmic FM, we are finding we are finding this performance is getting improved with compared with linear FM. And with quadratic FM, we are almost from logarithmic FM, some more performance is getting improved. And in the case of hyperbolic FM, we are getting the best performance that you can find from here. And now there is a property in hyperbolic FM, that is Doppler invariance property. So this is a little mathematics for that. So what it says is the instantaneous frequency of the transmitted signal should be equal to the time shifted version of the instantaneous frequency of the received signal. So we have done a mathematical proof in the paper, and based on that, what we got is here the time shift T0, that is time shifted version of the instantaneous frequency. That time shift is a constant. What we found out is that time shift is a constant, and hence we can prove that HFM is Doppler invariant. So these are the findings. These are the velocity change. We change the velocity from -50 meter per seconds to +50 meter per seconds, and the time shift is from -25 milliseconds to +25 milliseconds. So these are the results we observed from the plots what we got. For velocity changes, the signal is found to expand or compress. Also, a spread in the mass filter peak is observed. Symmetry is not followed in this case. For time shift, the location of the peak is getting changed, but for frequency shifts, what we observed is this peak is getting spread out, and this only HFM is showing Doppler invariance in this case. So the conclusion is waveform analysis based on narrowband ambiguity function definition shows that the effect of Doppler on LFM, logarithmic FM, QFM and HFM waveforms are similar in pattern, and its impact is minimal. On the other hand, waveform analysis based on wideband ambiguity function definition shows that the effect of Doppler on LFM, logarithmic FM, QFM and HFM waveform are drastically different, and its impact is very severe in all other waveforms considered except HFM, because HFM have the property of this Doppler invariance. Hence it is important to use wideband ambiguity function definitions while analyzing the impact of Doppler on waveforms, especially in the context of active sonars and underwater wireless acoustic communications. Systems where the waveform used are often wideband in nature. So these are our conclusions. That's all from the topic, and thank you.